Good morning, or good afternoon, or good night, or wherever you are around the world. My name is Per Gunnar Kjelsberg. I'm professor at Department of Electronic Systems at Norwegian University of Science and Technology. And I'm chairing this session on storage and emerging memory architectures. And we have a tight program, so I'll go straight to the first presenter. And we first have three 10 minutes presentations followed by 5 minutes questions, and then three 3+2 presentations. So pretty tight. And I'll keep a hard limit on the timing as well. So I will let the 10 minutes presenters know when there's 2 minutes left, and the 3-minute presenters when it's 1 minute left. So then the first presenter is Jiaojiao Wu, presenting adaptive switch on wear leveling for enhancing I/O latency and lifetime of high-density SSDs. Jiaojiao Wu received the Bachelor of Science degree from Southwest University, Chongqing, China in 2021. She is currently working towards her MS degree with the College of Computer and Information Science, Southwest University of China. Her research interests include NAND flash memory and computer architecture optimizations. So, please go ahead.
Thank you. Hello, everyone. This is Jiaojiao Wu from Southwest University of China. Today, I will present our work, which is about adaptive switch on wear leveling for enhancing I/O latency and the lifetime of high-density SSDs. This presentation has 4 parts. Let us start with the introduction part. Due to many advantages, NAND flash memory-based solid-state drives have become mainstream storage in varied-scale computing systems. We know the flash memory is composed of storage units. The form SLC flash memory, which storage unit can store a bit of data. Now it has developed to QLC, which a storage unit can store 4 bits. The biggest benefit of this is that storing the same amount of data requires fewer storage units, resulting in a lower price for flash memory. Due to the flash memory compact structure, however, the limit of P cycles of high-density SSDs decreases greatly, and thus impacts the endurance of SSDs. When a certain number of blocks in SSD reach a limited number of erases, the SSD will be scrapped. So in high-density SSDs, the next problem is a key issue. To solve this problem, a mechanism called wear leveling was proposed, and the goal of wear leveling was to delay the time of each block to reach the limited number of erases. If we do not trigger wear leveling, there may be some flash memory blocks that have to be erased frequently, and these blocks can easily break. Conversely, if all the flash memory blocks are taken care of together, more user data can be written. Next, our question is, how does SSD do wear leveling? Before that, I will throw out a few concepts. First is the code data. It is the data that users do not update frequently. Instead, hot data is the users update frequently. And next is the old block and young block. The old block is the flash memory block that has been erased more often. And the block with less erase times, we call him the young block. In general, because code data is not updated frequently, it is stored on young blocks, while hot data is stored on old blocks. Therefore, while leavening moves the code data to the block with more erases, let those older blocks take a break and free up the young blocks to replace the old to withstand the writing of user data. The traditional method attempts to carry out while leavening while approaching the constant threshold. However, such schemes need always keeping an even wire distribution of all blocks during the whole lifetime of SSDs, which must lead to more unnecessary data migrations. In order to solve this problem, adaptive while leavening is introduced in this context. It schedules while leavening by following an exponential tendency. We argue that adaptive while leavening can ensure good I/O responsiveness, but it brings about an I/O performance degradation at the later stage of SSD lifetime. To test the above conjecture, we did the following experiments. We performed an experimental study comparing while leavening with constant and adaptive threshold conditions, and the fact illustrates the response time of requests with the constant threshold of while leavening is relatively stable, even in the later stage of lifetime. On the other hand, adaptive while leavening can achieve good I/O latency at early lifetime, but worse I/O latency at later lifetime. Such observations motivate us proposing a new while leavening method to balance I/O responsiveness and the endurance of high-density SSDs. Yes, we have done this work. Then let me show you our design specifications of the work. The figure demonstrates the growth strength of different threshold function of while leavening, associating with the minimum erase count and the maximum erase count of block in SSD. Our proposed scheme performs in the range of two threshold functions of linearity and exponential. The linearity threshold function can ensure an approximate evenness of erase distribution and relative constant I/O responsiveness. The exponential function can reduce many unnecessary while leavening operations. For example, our proposal adaptively selects the threshold function from linearity 1 and exponential 1. And the adaptive switch while leavening employs the threshold function of linearity 1 in the case of the SSD device becomes idle. And it can adaptively switch the threshold function of while leavening to the exponential 1 model when SSDs become busy. Consequently, it can complete certain while leavening operations when SSD are idle. And it can relieve the pressure of while leavening in the later lifetime of SSDs. Then we have carried out certain tests to evaluate the proposed approach. We implement our proposal in the SSD SIM simulator, and the detailed information is shown in the figure. There are 4 evaluated methods: greedy, AWL, and AWL and utilization aware and our proposal. First, we will show the evaluation of lifetime as soon. The proposed adaptive switch while leavening can effectively improve the lifetime of SSDs compared to the related work.
2 minutes left.
Okay, and because varied while leavening schemes lead to different scales of lifetime, we present the result of I/O performance in 2 phases for compression fairness. And our proposal can adaptively perform while leveling once SSDs become idle, which can better minimize the I/O performance. The next is average I/O latency, and we can see in the second stage where our mechanism can improve performance by 27.6% compared to the related work. Finally, we recorded the number of while leveling counts under different mechanisms, and we can see that in the first stage, our proposal brings more operations compared to other adaptive mechanisms. In the second stage, the number of while leveling is reduced, indicating that our idle time to trigger in advance can effectively alleviate the while leveling pressure in the later stage and improve performance and life. Finally, let me make a brief summary on this work. Firstly, we propose a static while leveling mechanism which can adaptively switch the threshold condition for triggering while leveling operations. Then, we build an adaptive switch model, selecting the threshold function for performing while leveling with a dynamic manner by seeking a good balance between the real-time I/O intensity and the while differences of SSD blocks. And then we carry out comprehensive evaluation experiments by replaying the selected block traces of real-world applications on a simulated SSD device. As our measurements indicate, the proposed while leveling approach improves metrics of I/O response time and the lifetime of high-density SSD devices. Thank you for your time. Please contact us if you have any question.
Thank you very much. A very interesting speech. Questions from the audience? Anything physically from Shanghai? Oh, there's a question in the chat. What is the limitation for PE?
Thank you for your question. The PE cycle is erase operations for flash memory, and it can indicate one PE cycle. A program operation and eraser operation.
Hi, hello, can you hear me?
Yes, we can hear you.
Yes, yes.
Yeah. Actually, I have a question. I found in your experimental setup, the read performance and the write performance have a big difference. I don't know if there will, if we like the performance have, your setup have a big difference. Read performance and write performance. If our memory device doesn't have those big difference, and it will influence your experimental result.
Sorry, your voice is a little unclear.
Can you hear me?
Yes, but
we can hear you, but it's pretty hard to understand. And actually, the time for questions are now also running to an end. So I'm wondering if you can connect online in Gather Town or with questions otherwise.
Okay, I can check my questions.
Great, thank you very much. Then I think the next speaker, Jiali, you are in Shanghai, aren't you?
Yes, I'm in Shanghai.
Great. So then the next paper is Horae, a hybrid I/O request scheduling technique for near data processing based SSD. This is also, if I'm not mistaken, the best paper award candidate. So we are looking forward to listening to this paper. Jiali received his bachelor engineering degree from the College of Computer Science in Chongqing University in China in 2018. He is currently pursuing a PhD degree at the same place and have research interests including near data processing and smart storage. So please go ahead.
Now let's begin. So hello everyone, I am Jiali from Chongqing University in China. I'm honored to share our work for RRAM in Q6. First, I'll introduce the background of our work. The volume of data produced by us are growing rapidly nowadays. It's a great challenge to handle this data. In traditional storage architectures, it must be read from the storage to host CPU by the limited bandwidth of storage interface. However, with the data explosion, the limited bandwidth of storage interface is hard to overcome the data transfer challenges. So it is called the storage war problems. So a solution to solve the storage war problems is to move data processing functions into the storages, which we call it the near data processing NDP technologies. So by the help of the accelerators inside the SSD, the data need to be transferred to CPU could be processed before transfer to CPU, which can reduce the data volumes greatly. So NDP technology could solve the storage war problems. So this is a general architecture of NDP-based SSD. We mainly focus on two features of it. First, the NDP-based SSD need to handle hybrid requests, such as the normal. So we mainly focus on two features of the NDP-based SSD. First is that the NDP-based SSD need to handle hybrid requests, such as the POSIX request from the traditional applications and the NDP request from the NDP applications. The second is that the NDP-based SSD includes heterogeneous function units usually, such as the NAND flash module for storing data and the accelerators for the data processing inside of the SSD. So the two features of the NDP-based SSD occur the question. The different requests need a different function unit in different time. How to schedule them properly? Unfortunately, current NDP works ignore the hybrid task scheduling problems, which may reduce efficiency greatly. Let me illustrate the scheduling problems by example. Here are three different kinds of requests: read, write, and NDP request. If we schedule them on an NDP-based SSD, compared with the HCFS scheduling, the proper scheduling could reduce 59% of mixed time. So an NDP-based SSD scheduling method is urgently needed. So now I will show you our scheduling method for RRAM. According to our observation, the NDP and the normal I/O requests have more complex workflows, and each workflow is including many stages, and each stages in the workflow not only depends on the previous stages in the same workflow, but also depends on the dedicated function unit. So if we ignore the resource contention caused by the task blocking, if we ignore the resource contention, it may cause the task blocking, even if the needed function unit is idle, so make the restore function unit. So Horae, the idea is to reduce the task blocking caused by the resource contentions. Hence, minimize the uncritical stages into running on the uncritical function unit. The critical function unit means that the unit that most stages depends on, and the critical stages means that the stages that need to execute on the critical function unit. So Horae will give priorities to the critical stages within the critical function unit. So this is the overview of the Horae, including 2 steps. First, Horae will receive the request from the host and phrase it to get the request information, such as the request type and the block address. Then Horae will check if the request could fit in the DRAM buffer and change the prediction time, and then take different schedulings. After getting the request, Horae will build a DAG graph with multi stages for each request. The DAG graph is generated inside the NTP-based SSD. It is predefined when the developers developing the user NTP application. So after the DAG graph are generated, we will push it into the task list. And after the task list is ready, we will generate a priority-based execution sequence of stages. First, we will get the critical path dependencies, which denoted as the CPD value of each stages. The CPD value is the value that means the later how long will the later stages take after this stage finish. So the larger CPD is, the more critical those stages. So next, Horae will insert the each stages to the corresponding function unit stage list as a decreased order of CPDs. So after the execution sequence generated, Horae will next align the stages on the timelines according to the execution sequence we generated before, and line them on the timeline according to the intra-task dependencies. First, Horae will calculate the sum of CPDs of each function unit and takes the function unit with the largest sum of CPDs as a critical function unit.
2 minutes left.
So next, Horae will align the critical stages and its pre-stages to the timeline. If the stages, all parent stages has been aligned, it can align on the directed, but if not, it has to align its all pre-stages first. The last, when Horae align the stages on the timeline, it can be deleted. So that's all the Horae's workflow. I will show you our experiment. Due to the lack of NTP-based SSD, we built a simulator based on the SIM and Cosmos Plus, and we hybrid non-IO and NTP request as a hybrid workload, and we take FCFS and NTP first and some other SSD scheduling as the comparisons. First, I will show you the effect on the performance. So Horae could, as we can see on the slides, Horae can constantly outperforms some other existing algorithms on all workloads. On average, compared with the FCFS, Horae can reduce 11% of the misspan. So next, we change the ratio of read and write requests. As we can see with the increase of the ratio of IO tasks, the effect of Horae can gradually approach FCFS. And then we test the resource utilization. Resource utilization is divided the ratio of the sum of the running time and the next time. So the higher the parallelism, the higher the resource utilization. So Horae can achieve the 7% improvement on resource utilization. So let me take a conclusion. NDP-based SSD is a promising technology to solve the storage problems. Existing NDP works ignores the hybrid request schedules. So we propose the scheduling technique for hybrid request scheduling and can reduce 11% of mix on average. So that's all my presentation. Thanks. Any questions?
Thank you very much for your presentation. Questions from online or from in Shanghai?
There is a question in Shanghai.
Thanks for your talk. It is a great work. So I have a question. As your evaluation, you present some results on different task ratios. So did you conduct experiments on some real workloads or some real applications? Thanks.
The normal I/O workload is collected from the open source, and the NDP workload cannot be available nowadays. So we installed some NDP works on our platforms and collected the workload. So we covered them in some different ways to measure the performance. So, any questions?
We also have one question in the chat. What are the functions in the SSD?
But it's a function. The function means the function unit, because NDP technologies could handle many different tasks, such as the GDISC work could solve the graph computing inside the SSD, and the React work could solve the pattern matching tasks inside of the SSD. So the different NDP works including different function units. So that's what function means. So it will usually be a hardware accelerator.
Thank you very much. Then I think we move on to the next speaker, unless there are more questions. And the next speaker, I think, is online again. This time it's Gokul Krishnan, and the paper title is Hybrid RRAM SRAM in-memory computing for robust DNN acceleration. Gokul Krishnan received his Bachelor in Electronics and Communications Engineering in 2016 and a Master in Science and PhD degree in Electrical Engineering from Arizona State University in 2021 and 22. In between, he has also worked with Apple Incorporated. His current research interests include different aspects of deep learning. He is a recipient of the Richard Newton Fellowship at the DAC in 2020, the Joseph A. Barkson Fellowship for 2020-21, and the GPSA Outstanding Research Award winner in 2021. So we look forward to your present, Gokul. Please go ahead.
So can you hear me properly?
Yes, thank you.
Hello. Oh, yeah, thank you. Hi, good morning, good afternoon, good night, good evening to wherever you are. My name is Gokul Krishnan, and today I'll be talking about our work, Hybrid RRAM SRAM in-memory computing for robust DNN acceleration. This work was done in collaboration with between Arizona State, IBM, TJ Washington Research Center, and SUNY Polytechnic. So, this is the outline for today's presentation. We'll first look at the motivation of this work, and then we'll do a deep dive into the hybrid IMC architecture. We'll then look at the hybrid IMC training framework for the architecture. We'll then look at some of the key results and then conclude the presentation. So the motivation of this work stems from the fact that resistive RAM or RRAM-based IMC acceleration suffers from many non-idealities, such as read and write variation, limited precision, stuck-at faults, amongst many of the others. In addition, quantization of the neural network, which improves the hardware efficiency, increases the effect of these non-idealities significantly. Conventional variation-aware training methods, which have been proposed in prior works, are unable to recover the accuracy to the original point, which is the floating point 32-bit model, in the presence of quantization and RRAM variations. The figure on the right shows you the accuracy with the RRAM IMC macro for 3 different networks. You can see that for a quantized network, along with the conventional variation-aware training method, for smaller networks such as Resident 20, there's a drop of about 16.5% from the baseline model, while for larger data sets such as ImageNet with Resident 18, it's about 27.8%. So there's an urgent need to actually address this drop in accuracy for resistive RRAM-based IMC accelerators. To address this, we propose the hybrid RRAM SRAM IMC architecture. The principle of this work stems from the fact that we're actually going to combine the 2 outputs from 2 MAC structures and then utilize ensemble learning. So the noisy output from the RRAM IMC is added to the clean output from the SRAM IMC, which has a shifter in its data path in order to have different levels of compensation to generate the final output. This is done on a layer-wise basis. The figure at the bottom right shows you the overall block diagram of the architecture. It consists of an RRAM macro, which has an RRAM IMC array and its associated peripheral circuits, an SRAM macro, which has a MAC array, a buffer, and an SRAM memory, and a programmable shifter, which allows for different scales of compensation for the RRAM output. We also have a control logic, an input-output buffer, and an adder. Let's now look at the RRAM macro. It consists of an array of 1T1R RRAM cells, which form the IMC array. A custom bitline, select line, and column mux are designed which have reduced resistances. We have a PMOS header that is utilized for the readout circuit. We utilize custom RTL for the decoder, which is the RRAM decoder, and have a word line driver and level shifter. We also utilize input-output buffer to control the activation movement. And we design a low impedance PMOS header and a 3-bit ADC, considering the bitline swing and the resolving ability of the ADC. Next, let's look at the SRAM macro. It consists of an array of processing elements of PEs, an SRAM array which stores the weights, and a buffer which controls the activation moment. So the SRAM memory actually stores the compensation weights, which are used for the clean output from the SRAM MAC. We utilize an output stationary structure for the PE with a custom control logic. So basically, we reduce data movement and enable parallel computation while consuming data in each cycle without having to move data across PEs. We also use the input-output buffer to handle the data transfers in and out of the macro. Let's now look at the programmable shifter. The shifter supports up to 3-bit shift in the SRAM macro output, which allows for different scales of compensation. Let's just take one example to go through it. So consider the case having a 2-bit SRAM and a 2-bit RRAM. In the case we have no shift, both the SRAM bits compensate for both the MSP as well as the LSP with the RRAM output. In the case of a 1 shift, we just compensate for the LSP, not the MSP, but we increase the dynamic range by introducing an extra bit. In the case of a 2-bit shift, we actually do not compensate for any of the bits individually, but we have increased dynamic range due to the 2 bits of the SRAM. A similar case is seen in the case of an 1-bit SRAM and a 3-bit SRAM. Let's now look at how we enable the hybrid IMC architecture. We first design a full training framework. We extract RRAM models from a 65 nanometer device, which is at the wafer level. So you can see here the HRS as well as the LRS. The HRS has a higher variation as compared to that of the LRS. At the bottom, you can see the RRAM resistance measurement for different compliance currents. So here we basically look at the maximum amount of levels that we can access within the RRAM, such that we can store different number of bits within it. So as we add an extra bit into the entire RRAM, we add a specific amount of variation at a bit level to make it as coherent to the actual hardware as possible. Let's now look at the training framework. So we utilize a couple of inputs such as the RRAM precision, SRAM precision, the shift scale, activation precision, the SRAM pruning group size, which I will talk about in a few slides, the training epochs, and the RRAM variations. So first, we randomly initialize the weights of the neural network, perform in-training quantization, and save a quantized model A. The quantized model A is then loaded, and we add RRAM variations and perform IMC-aware training, where we break up large convolution to small convolutions depending upon the size of the IMC crossbar array. We add the bit serial computing effect and also the ADC quantization, and then store a model B. Next, we create a parallel model to that of the SRAM to that of the RRAM model, which forms the SRAM model. We freeze the RRAM weights and then combine the output from the SRAM model and the RRAM model in order to generate the hybrid architecture. But in this case, we only perform backpropagation for the SRAM path, and then we generate a model C. Finally, we take this model C, we keep the RRAM weights still frozen, and then prune the SRAM weights such that we can reduce the overall overhead from the SRAM macro in order to generate the final model D. In this slide, we look at the 65nm test chip that was designed. The figure on the right shows you the layout of the test chip. So it consists of one RRAM macro with a 64 by 64 1T1R RRAM cells and associated peripheral circuits. We have one SRAM macro with 2 kilobit SRAM, 16 MAC engines, and a control logic. The readout of the SRAM is matched to the total number of MAC engines we have in order to achieve maximum parallelism. And then we have an overall control logic built into the RRAM decoder along with a scan chain for testing. Let's look at some of the key results. First, we'll start with a case where we analyze the SRAM compensation without any shifter. You can see that a higher SRAM precision leads to a higher compensation and higher accuracy. But at the same time, having a higher RRAM precision, which means that we have more bits within the weights, results in a lower SRAM precision requirement in order to have the maximum amount of accuracy. It is also to be noted that a higher SRAM precision leads to more overhead. We now look at the pruning of the SRAM macro. So the figure at the bottom shows you the post-mapping accuracy and the SRAM pruning ratio for ResNet 20 and CIFAR10 at different RRAM precisions and SRAM precisions. We also analyze this at two different pruning group sizes. So we form a group by looking at the output channels, or that is combining along the output channels in order to have, in order to enable the output stationary structure within the SRAM.
2 minutes
so here
left.
You can see that at a lower RRAM precision, we are able to prune very less, while as we increase the RRAM precision, we can prune more SRAM, while at the same time having a lower pruning group size allows us to have a higher pruning ratio. Here we look at the comprehensive accuracy results. You can see that consistently across different networks and different datasets at different levels of precision, at a high SRAM pruning ratio, we are able to achieve improvement in accuracy over conventional VAT methods. Here we look at the SRAM macro overhead, which is the area overhead, power overhead, training time overhead, and the memory overhead. You can see that we incur only up to 20% overhead in area, 2.6% in power, 25% in training time, and 24% memory overhead. And this is only for mobile net V2 on ImageNet. The increased overhead is attributed to the smaller size of the network and the large size of the dataset. Now, comparing with prior work, you can see that consistently the proposed hybrid IMC architecture achieves higher accuracy, which is up to 21.9% improvement on ResNet 20, 12.65 MBG 60, and 6.52 on ResNet 18, all at a lower activation precision and a weight precision. To conclude, we propose a novel hybrid IMC architecture with an RRAM and SRAM macro for robust DNN acceleration. We developed an associated training framework to support the architecture. Experimental evaluation shows up to 21.9% and 6.52% improvement in post-mapping accuracy. And through this architecture, we open up the opportunity for a realistic multi-level RRAM IMC architecture for DNN acceleration. Thank you. And I'm open to questions.
Thank you very much. Questions online or from Shanghai? No questions? I have one regarding your test chip. Could you say something about the difficulties of producing the chip and yield problems and stuff like that related to the chip you have made?
So yeah, actually, the yield problem is one of the issues within RRAMs that we have seen. In terms of designing a test chip, it's not really that difficult because there are certain custom blocks which we have, but the rest of them are automatic placed en route. In terms of actually getting the chip back and looking at it, yes, you are right. There are certain amount of yield issues we have been seeing within them. And this is something we need to improve from a process standpoint. But the proposed method stands, as is. It would work in this case, or even if your yield was, even worse than what we see.
Thank you very much. Other questions? Okay, but then I think we will continue going over to the three work in progress papers. The first one is presented by Minas Abedin, and the paper title is A Processing in Pixel Accelerator Based on Multi-Level HFOX RRAM. Abedin is pursuing his PhD at the College of Nanoscale Science and Engineering in New York, USA. His research focus is on non-volatile memory device resistive random access memory for AI training and inference. For this project, he collaborated actively with New Jersey Information and Technology Assistant Professor Shahin Anghisi and Arman Rudi from University of Nebraska-Lincoln. So please go ahead.
Thank you, Professor. Hi, everyone. This is Minas. Welcome to our presentation on a processing in pixel accelerator based on multi-level hafnium oxide-based RRAM. So basically, the idea of this project or work is to reduce the data transfer, like my previous authors talked about. So the idea is if you can reduce the data transfer from where it's generated, you can reduce the data transfer bottleneck, which is the time to send it, also the energy efficiency. So in our work, we try to have the neural network accelerator as close to the sensor chip as possible, which is in the image sensor or in the pixel. And we use RRAM, which is a non-volatile memory, and also have the capability of doing MAC operation. We included the RRAM cells inside the pixel, and we designed our custom input encoders to support that. So what it does in a complete array is the pixel circuit is generating the signal as soon as that the input encoder encodes it for the RRAM cell to do the MAC operation acceleration. So we also use the multi-level RRAM cell capability so that we can have the larger weight bits so that the accuracy of the neural network increases. So this is not the first paper that's written for the in-pixel accelerator, and our work actually shows higher accuracy and closer to the baseline for different data sets, as well as our efficiency is much higher than the other papers. So with that, I will conclude my work in progress presentation.
Thank you very much. We have time for a couple of questions, and I also like to mention that your poster, you will present your poster at poster sessions later today, so it's also possible to go into GatherTown and meet you there, I assume.
Yeah.
But we can also take questions here. One very quick one from my side, partly related to the one I had, the previous one. Have you looked into making test chips?
Not for this one yet. So we're still looking at different pixel circuits so that like this is a work in progress. So we are thinking there might be place for improvements. And then we're gonna try to do fabrication.
Thank you very much.
Mm-hmm.
And now I actually see that I missed up the order of the work in progress papers. Thank you for saving me by just hopping in and doing your presentation. I see now that it should have been Alexander Rowe, that had the first work in progress presentation. His paper title is Efficient Low Latency Near Memory Addition. He graduated from the University of Kentucky in May 2022 with a Bachelor of Science in Computer Engineering. He has been performing research with Dr. Saeed Saleh since June 21. He is currently resident in Naperville, USA, and works in automotive engineering. So then I guess you can take over, Alexander. I'm sorry about that.
Oh, that's all right. Hi, my name is Alex Ray. This is our work in progress paper, Efficient in Memory Carry-Free Addition. For this paper, we're using a processing and memory paradigm so that we could reduce resources used in both power and time that it takes to move memory out of memory into a processing array, then perform arithmetic on it and move it back into the memory. We wanted to design a circuit that could do activities like arithmetic directly on the memory cells. We also combined this with resistive RAM and phase change memory technologies that allowed us to include more than one bit in a single cell. But because we found some difficulties with using 2 bits per cell in terms of reliability, we used a 1.5-bit MLC schema, which allowed us to use ternary logic. And then in addition to this, we used a stored number transfer representation algorithm, which allowed us to perform carry-free addition. And the carry-free addition is handy because that allows us to do parallel addition on all of the bits at the same time. So to use this, we took the algorithm that uses STNR. The disadvantage of STNR is that it is a redundant number system, so there are multiple different ways to write the same number. But the thing that is useful about it is that through an algorithm, it does allow us to do carry-free addition. So we took these truth tables here that describe the way that the algorithm works, and we created circuits that would implement each truth table. The algorithm works in 3 phases. The first 2 phases each produce a sum digit and a transfer digit, and then the third phase produces just one sum digit, and it is the total sum of the whole calculation. So for the C2 circuit, we were able to use Karnaugh maps to derive ternary logic gates straight from the truth tables. And then for our other circuitry, which provides the sum digit, we were able to optimize this slightly by implementing a counter that counts the number of ones that are input, which reduces the number of transistors that are required by 35%. And C1 can also be used to calculate the sum digit that is produced by stage 3 with the minor modification shown in red with the addition of a multiplexer. So C2 allows us to calculate the transfer digit for both the first and second phases, and C1 allows us to calculate the sum digit for all 3 phases of this process. We then are able to take these 2 circuits and attach them to the memory rows in such a way that they can process in a set number of memory cycles. Since it's parallel bitwise addition, there is no increase in the time it takes to add 2 numbers together on the number of bits that are in the 2 add-ins. So we were able to come our way with a constant 21 cycle time for addition. And here we compare that to 2 other adders that are modern adders. And in this graph, we show how the number of bits of the add-ins increases the number of time of other adders to calculate the sum, and ours stays constant. And then some future work we'd like to do on ours to perhaps decrease the number of cycles ours takes further, and to do parallel addition of multiple pairs of numbers stored in 2 rows of memory instead of just the 1. Thank you.
Thank you very much. Quick and efficient. Questions, audience, or chat? I guess everyone is saving up for coming to the poster session and ask difficult questions there.
Mm-hmm. Unfortunately, I won't be able to be available at the poster session later today.
Okay, so then certainly if you have questions, please come up with them now. Okay, there doesn't seem to be questions, and I must admit that this is not my special field of expertise either, so I didn't quite manage to come up with a difficult question for you, but I'm sure you are also willing to receive questions on email if people are wondering about your work.
Yes, absolutely.
Okay, then I think we go to the final work in progress paper, which is then going to be presented by Anand-Preet Kaur. He is currently in his 4th year of the PhD program, Department of Information Technology at the Indian Institute of Information Technology, Allahabad in India, where he's also a member of the System Lab group. His research work broadly includes security of embedded devices, and he has been a recipient of the Government of India Ministry of Human Resources MHRD Fellowship. So please go ahead and present your work.
Hello everyone, my name is Anand-Preet Kaur and I am a PhD scholar at Systems Lab IIIT Allahabad. Today I am here to present my work DRAM Address Mapping Unveiling Truth for ARM Devices. This is the outline of my presentation. Hardware vulnerabilities existed for a long time, but in 2014, a critical hardware vulnerability, Roadhammer, was reported, and it caused unexpected errors in DRAM. A very strict requirement to mount a Roadhammer attack requires the knowledge of underlying hardware address mapping. This is the way DRAM is organized. However, the memory geometry information is not made available by major public vendors. To get this information in literature, 2 ways are suggested: hardware podding and software approaches, and that too have been explored for Intel-based platforms. To the best of our knowledge, only 2 software-based approaches have been proposed for DRAM geometry exploration for embedded platforms, but that disclose only a limited memory geometry information, which is not sufficient to mount a deterministic Roadhammer kind of memory attack. So this is our motivation. Majority of embedded devices use ARM architecture, which has different instruction set compared to Intel-based. So we cannot directly apply the proposals of Intel on ARM as they have privileged instructions. So we propose a software-based methodology to infer the mapping of DRAM modules associated with ARM processors. So our proposed methodology is based on basic principle that if a pair of addresses happen to present in 2 different rows of the same bank, they are accessed alternately, and if there can be a root buffer conflicts which take more memory access time. So this is the workflow. It consists of 3 modules: the latency module, which acts as a kernel module. It has access to privileged instructions. It finds out the latency between pair of addresses, and then via communication module, it passes it to the main module. So it consists of 2 major components: address generation and translation, and physical to DRAM address mapping. Firstly, we generate a large pool of virtual addresses, and then they are translated to physical addresses via page map interface. And then to uncover the physical to DRAM address mapping, first of all, we find the row bits. We select 100 pair of addresses that differ only at one particular bit location. If the access latency is higher than the threshold, we consider them as row bits. Similarly, for finding the column bits, we select physical addresses that differ at 2 bits. One is the found row bit and another is the non-row bit. If the access latency is higher than the threshold, we consider them as a column bits. Then to identify the bank bits, it consists of 3 phases. Firstly, the physical addresses that are selected that cover the possible range of bank bits. Then these selected physical address bits, we split them into bank number of files, and then we apply the XOR mask and get the final possible bank address functions. We validated our proposed method on Raspberry Pi 4B, and these are our preliminary findings. To conclude, I would say as there is a need to explore Roadhammer on embedded devices. For the same, we require the memory geometry information, and we propose a tool DRAM mod which infers the memory geometry information of underlying hardware. Future work includes the validation of the proposed methodology by performing Roadhammer tests and comparison with state-of-art proposals. These are the references. Thank you.
Thank you very much. And that was our last speaker. Questions from the audience in Shanghai or on the chat? You will be at the poster session later today, I guess.
Yes, sir.
That's great. So then you can also ask questions there. Any questions for now? Okay, there doesn't seem to be. Then I think we are precisely at the end with respect to timing as well. So I would like to give all the speakers thanks for your good presentations, and a big applaud from everyone. Any final inputs from Shanghai? Alireza or anyone else? Anything from you? Okay, then once again, thank you for attending this session. It was a lot of good presentations, and see you later at a later session or at the poster session. Bye-bye, everybody.